Um, Hello everyone. Today we have Will Dudarov, and he's going to talk about this conjecture from the Combinatorics of Weyl group multiple Dirichlet series Orange book. Thank you for coming.
Thank you very much, Slava. I'm not sharing. Sorry about that. Hello, my name is William Dudarov. I'm a student. I'm an undergrad at University of Washington, Seattle. And this summer, I worked with Ben Brubaker and Andy Hart in their project group in the Polymath Jr program on just kind of tackling the like a bijective proof of the proof presented in Weyl group multiple Dirichlet series type A Combinatorial Theory by Brubaker, and Friedberg. And so this is the culmination of those efforts. We had a big group. We had a lot of very cool, very talented, wonderful undergraduates that I worked with. They all contributed a lot. And here they are. So I wanted to recap a lot of basic definitions towards the beginning of this talk. So recall that specifying Weyl group multiple Dirichlet series for chosen data P and F S M, where P is a reduced root system of rank R. In the book, it's type A. N is a positive integer. F is an algebraic number field containing the group of two roots of unity, etc., is equivalent to just working. Is equivalent to specifying the p parts of this function h c m. And for more information about that, see like the very first page of the Orange book. And then the Orange book then gives two natural combinatorial definitions in terms of the p part of HCM in terms of Gelfand-Saitlin patterns. And these two combinatorial definitions they call H gamma and H delta. So we'll see what those are a little later. First, recall a Gelfand-Saitlin pattern of rank R is a triangular array of non-negative integers that looks like this. And the entries in this triangular array interleave. So this entry is between this one and this one. I don't know if you can see my mouse.
Yeah, we can.
Perfect, thank you. This one is between this one and this one. This one is between this one and this one, and so on. And so let's pick a top row, 2, 1, 0. Here are all 8 possible GT patterns. We can just call them GT patterns. Notice that they don't really have to be strictly decreasing in a row. We can have repeated entries in a row. And we'll see why that kind of causes problems in our context. So I want to define these natural definitions of the p part of H. These definitions, H gamma and H delta. First, we take a Gelfand-Saitlin pattern, tau. So it's one of those triangular arrays of integers. We first define the following functions on the entry of tau. So you take an entry, you apply f gamma, you get 1 if the entry is equal to its top right neighbor, the top left neighbor, 0 if it's equal to both top neighbors, and v plus 1 or 1 plus v otherwise, where v is a formal variable. And similarly for delta weights, take an entry, v top right, 1 top left, 0, both 1 plus v otherwise. And so you take the whole Gelfand-Saitlin pattern tau, and you for every entry, you multiply up these f gamma, f delta, and you get these statistics g gamma, g delta. And finally, with all this in mind, h gamma is equal to the sum over tau fixed top row of g gamma tau g, and h delta is the sum over tau with fixed top row of g delta tau. And so for type A, the big result in the orange book is h gamma equals h delta. So we have these sums equaling each other. And in fact, for strict Galton-Salem patterns, so those without repeated entries in a row, this one's strict, this one's strict, that one's strict, this one's strict, this one is not strict. It actually holds that you don't need the sum. There actually is, for a given tau, you take the g gamma, there exists a tau prime, which has the same g delta, and the g delta of tau is equal to the g gamma of tau prime. And that tau prime is just the what's called the Schützenbergian evolution, or the evacuation of tau. That was something that was originally defined for standard Young tableau, but then defined for Galton-Salem patterns by Kirillov and Bernstein. And so going back to our top row 2, 1, 0 example, to kind of focus on this bit, take this tau, there exists a tau, you apply the Schützenbergian evolution for the evacuation, you get this, and in fact, g gamma of this equals g delta of this, take the g gamma of this, take the g delta of that. And this holds for these non-strict patterns, but for these strict patterns, but then when you take the Schützenbergian evolution of this, you get a non-strict pattern, and then the g gamma, g delta of this is not equal to the g gamma of that. So the motivation for this work is just that the Brubaker-Friedberg proof isn't bijective because of non-strict Galton-Salem patterns. The fix, possibly is refining, Galton-Salem patterns and then seeking a bijection with these refined Galton-Salem patterns, which was what we tried to do at the very beginning of our efforts, and that wasn't very good. That wasn't very fun. We decided to work with lattice models instead. Recall, you may have read the chapter Metaplectic Ice in the book Multiple Dirichlet series, All Functions and Automorphic Forms by Brubaker, Chinta, Friedberg, and Gunnels. Brubaker, Chinta, Friedberg, and Gunnels provide a bijection between strict Galton-Salem patterns of fixed top row and admissible states of square ice, or Takayama ice, or the 6 vertex model states with fixed boundary conditions. So it thus suffices to work with Takayama ice or 6 vertex lattice model states when one wants to work with strict Galton-Salem patterns and Schützenbergian evolutions. So you can kind of like define maybe a Schützenbergian evolution on Takayama ice. So, but in the literature, there's a lot of other very cool generalized lattice models that have been described. Takayama ice is interesting because its partition function yields like spherical Whittaker functions over GLR. But then, generalizations of Takayama ice also yield other interesting, like kind of generalizations of Whittaker functions over metaplectic covers on metaplectic covers uh, Iwahori-Whittaker functions. So if you just take Takayama ice, the partition function, you'll spherical Whittaker functions. If you have a statistical charge, you get like what's called metaplectic ice, and that gives you like metaplectic Whittaker functions. So spherical Whittaker functions on metaplectic and covers of GLR. And yeah, color, like that's been described, like colored lattice models have been shown to provide Iwahori Whittaker functions, and then most recently there has been color and charge mixed together in a lattice model, and the partition functions on those yield metaplectic Iwahori Whittaker functions. And so our models try to refine our refinements of all of the above, and are very extremely promising candidates to yield a bijective H gamma equals H delta proof. First, I wanted to mention bicolored lattice models, symmetric lattice models. So these work for non-strict delta unsettling patterns. So this is actually a bicolored lattice model in bijection with, well, a lattice model state in bijection with the non-strict delta unsettling pattern 0, 1, 1. And we originally kind of conjectured that like kind of these are a good, like these bicolored symmetric lattice models are a good candidate for a to find a bijection, but they're not very powerful. They don't give us like the metaplectic case, which is what is covered in the Orange book, and that's what we really want. There's kind of not enough like gamma and delta vertices and stuff to give us uh, partition functions that are metaplectic Iwahori Whittaker functions. So this is bicolored lattice model, admissible vertices and their Boltzmann weights. So our group introduces charge to these. The metaplectic Iwahori Whittaker function and ice paper. I can't exactly remember the exact authors, but I think it was Brubaker, Bump Gustafsson. Like they use like pretty similar looking models, but with bicolorings. But in the end, it's just one color and like a charge statistic. So our models as statistics use color and supercolor and charge. Colors move down to the right. Sorry, this is a little long. Supercolors move down to the left. Every horizontal edge has either a color or a supercolor, and every vertical edge either has both a color and a supercolor, or it has neither of those. So neither color nor supercolor. And it also has a charge statistic. So we have this function. We fix an n positive integer greater than or equal to 1. We have a function g of a, where a is an integer mod n. And we have these restrictions on it. G0 equals v, and GA times G minus A. These are mod n, of course, equal negative V if A is not equivalent to 0. And so in the gamma bicolored charged model, the dashed horizontal edges have, there's something in the chat, maybe worth mentioning that H gamma dash. Yes, that's correct. The dashed horizontal edges in these models have charge. So here the admissible vertices and Boltzmann weights. So C is greater than D. These are solid colors, and E is greater than that. Those are dash colors. We have the following, admissible vertices and the following Boltzmann weights for them. And they kind of depend on A. Okay, so a superscript star equals A, except for one case. So here you have a superscript and an A. Those are the same unless we are at a superscript star is A plus 1 mod n when at the leftmost column of a big column being one of these big columns. So leftmost over here, like here. And in the, sorry, that's typo, in the delta bicolored charged model, the solid horizontal edges have charge. So here the admissible vertices, they look pretty similar. The A's are all swapped around. The Boltzmann weights are swapped around in the bottom row here. And the thing is, to get this metaplectic case down, like Andy determined that Andy Hart determined like these are the only weights that work. Nothing works if these are not. Well, like these are the exact weights that have to be. These are the admissible vertices that have to be. And a lower star here equals A, just as kind of before, but we set a lower star equals A plus 1 when at the rightmost column of a big column. So perhaps like right, okay, sorry. And so let's work through an example. This is a wonderful example that Andy wrote up. So we choose n equals 2, and we have two possible values of A then, since A has to be 0 to 0, 1, and we choose a partition 3 and 0, and then we just look at one state. The following are bicolorly charged gamma and delta lattice model states, respectively. First, the gamma lattice state. Here it is. As you can see, it's basically a bicolored lattice model with solid colors, stacked colors, and then the statistics, the charge statistics on the dashed colors. They're mod 2. Since they're on the dash statistic, and on the dash colors, that means they're, this is in fact a gamma lattice model. And if you recall the Boltzmann weights and the initial vertices that we had and their respective Boltzmann weights, all of the Boltzmann weights here are 1 except for the decorated vertices. So the triangle here, if we go back and look at the chart again, that has weight 1 plus v, and the square and the diamond have weight g1, g of the charge. Therefore, the weight of this entire state, of this gamma bipolar charge lattice model state, is g1 squared 1 plus v. Now let's look at a delta state. So as we see the charge goes along the solid colors, we're calling our delta admissible vertices, and they're both units. We see that all vertices have weight 1, except for maybe the decorated ones. But we see that if we go back and look at the chart, the triangle actually has weight 1. The square has weight negative v, and the diamond has weight 1 plus v. Therefore, the weight of this delta bicolored charged lattice model state is minus v times 1 plus v. These are not the same. Minus v, 1 plus v is not the same as, g1 squared 1 plus v, but it actually is. So if we recall the rules for our function 2a, for fixed n plus 1, and greater than or equal to 1, we have a function g where a is an integer mod n, and here is 2. G0 equals v, g of a times g of minus a equals negative v if a is not equal to 0 mod n, or 1 is not equal to 0 mod 2. In fact, negative 1 is equivalent to 1 mod 2. So we have g1 squared equal to g1 g minus 1, which is by this equal to negative v. So we do indeed have a correspondence here. So that's just one example of this matching. Hopefully, there exists a bijection between gamma and delta bicolored charged lattice model states. So we have to talk a little bit about refinement. Indeed, these definitions of bicolored charged lattice models refine the definitions of bicolored or symmetric lattice models. We have also proven that the bicolored symmetric lattice models refine uncolored lattice models. Thus, these bicolored charged lattice models refine uncolored lattice models. And so we can finally, with all of this in mind, we can now state the main conjecture of this project, and that is that exists a weight-preserving, a statistic-preserving, weight-preserving bijection between gamma and delta bicolored charged lattice model. That's an mouthful. Maybe we should shorten it to something else. Bicolored charged lattice model states with fixed boundary conditions. And so the next steps are, look for that bijection, find that bijection, prove that that bijection is a bijection on these special bicolored charged lattice model states. And then prove solvability by showing this satisfies the our model satisfies the Baxter equation. In conclusion, as Ben said in one of the previous talks in the seminar, day M1, then 1. Beyond mountains, there are mountains. There's a lot more to do with the Hessian proverb. And here are my references. Thank you very much.
Thank you so much for your talk. Okay, let me stop recording.